Good day, dear participants of the conference. With your permission, I present a work, Neuro-Fuzzy Methods for Detecting Sensor Failures in Helicopters' Turboshaft Engines. The movement control of modern helicopters faces significant uncertainties in parameters, flight modes, and environmental conditions, alongside potential emergency situations such as engine failures and structure damage. To address fault tolerance in helicopter control, two primary aspects must be considered: the configuration of control algorithm during failure situation and the simulation's identification of failure occurrence, nature, and source. Sensor failures in helicopters' turboshaft engines pose significant challenge as they provide critical information for helicopters' movement control. Classical failure detection methods encounter difficulties stemming from nonlinear models, measurement inaccuracies, and large data volumes, alongside issues of signal-to-noise ratio and computational complexity. Moreover, classical methods often require system model linearization and simplification, which may not align with the task's complexity. Neural network method, particularly Neuro-Fuzzy network, emerge as promising solution for fault-tolerant control, offering advantages is our common classical method's limitation. Neuro-Fuzzy network demonstrate effectiveness in identification tasks, highlighting the need for developing Neuro-Fuzzy methods for detecting helicopter turboshaft engine sensor failures. Timely detection of failures can prevent emergencies, while a neural network failure classifier enhances diagnostic accuracy, reduced helicopter downtime, and complement traditional monitoring and diagnostic techniques, enhancing overall efficiency. The computation of helicopters' turboshaft engine thermogas dynamic parameters, a compressing air intake in the combustion chamber, specific engine output, and the fuel-to-air consumption ratio within the chamber is accomplished through a neural network model specifically designed for helicopters' turboshaft engines. This model, developed by this authors group, is presented on this slide. The transition to employing Neuro-Fuzzy network signals a promising direction for enhancing the mathematical modeling of helicopters' turboshaft engine, enabling improved efficiency and precision in controlling and monitoring their activities. The adaptive Neuro-Fuzzy network inference system ANFIS, Adaptive Network-Based Fuzzy Inference System, is a hybrid multi-layer artificial neural network of a special structure without feedback and presented on this slide. The hybrid method of training the Neuro-Fuzzy network, ANFYS, was proposed through the use of the ADAM method as a gradient-based optimization algorithm, as well the adaptive k-means clustering methods for optimizing the shape of fuzzy membership function. The following helicopter's turboshaft engine thermogas dynamic parameters recorded on helicopter board are used as input data in this work, reduced to absolute parameters according to the theory of gas dynamic similarity. Gas generator rotor RPM, gas temperature in front of the compressor turbine, free turbine rotor speed, fuel consumption. To train in a Neuro-Fuzzy network, we employ a hybrid network training approach which marks the ADAM method with the modified inverse gradient descent methods. The training process comprises a specific number of circles now an epoch set at 30 and 50. The evolution of the model's accuracy in construction a fuzzy inference system relied on the root mean square error metric assessed across both training and testing data sets. This slide presents the results of a computational experiment which was a simulation of identifying and determining the location of a phallic gas temperature sensor in front of the compressor turbine. Since the failure is abrupt, the additive and the moment of its occurrence, there is a sharp deviation from the standard behaviors for the temperature of the gas in front of the compressor turbine. To make the algorithm resistant to false positives caused by modeling errors and noise, thresholds and introduced for each neural network model according to the expression that takes into account the average value of the performance indicator and the standard deviation. These tables present a comparative evolution of the accuracy of conventional and Neuro-Fuzzy approaches in failures classification. They illustrated the likelihoods of the first and second type errors in classifying faults, including measuring channels failure in gas temperature preceding the compressor turbine, gas generator rotor RPM, and combustion chamber defects. The data provided in these tables affirm that intelligent techniques exhibit superior efficiency in detecting faults within engine components and subsystems. This table shows the results of calculating the coefficients of erroneous and qualitative identification of failures and defect, gas temperature in front of the compressor turbine sensor failure, failure of the free turbine rotor speed measuring channel, gas generator defect, combustion chamber defect. The conclusions are presented in this slide. Thanks for attention.